Swayam Prabha. Digital India. Educated India.
Hello, welcome to NPTEL NOC, an introductory course on Point-Set-Topology Part-II. So today we will study Wallman compactification, module 34. As motivated last time, we shall make a blanket assumption that the space x tau is a T1 space. As before, let Wx denote the collection of all ultra closed filters on X. We also have introduced this map function phi from X to Wx, namely taking any point X, take the atomic filter Fx, which we know that it is ultra closed filter because X is a T1 space. We propose to topologize Wx so that the pair phi comma Wx becomes a compactification of X. Recall, the compactification is actually an equivalence class, but we keep on saying that you pick up any representative, that is also compactification. And the compactification satisfies that the map phi from X to whatever space you are taking is an embedding such that the image of that embedding is dense in the whole space. Okay? The whole space Wx is compact. So these are the conditions I am just recalling, that's all. So going towards topologizing Wx, let us introduce some notation here. For each subset A of X, define A plus to be all ultra closed filters in X which contain A. A must be an element of that. A is an element of this ultra closed filter. So this collection of all such ultra closed filters will be denoted by A plus. The following lemma on this notation is very simple but very useful also for us. A is in F if and only if F is in A plus. So this is the definition of A plus. Empty set plus is empty because no filter contains empty set. X plus is the whole space because all ultra closed filters, in particular all filters contain X. So these are straightforward. A intersection B plus is A plus intersection B plus. So this needs little bit seeing how. Take a ultra closed filter which contains the intersection. Then just by being a filter, it will contain both A as well as B. Therefore, that ultra closed filter belongs to A plus as well as B plus. Conversely, if a ultra closed filter contains A as well as B, then the intersection, again being a filter, the intersection will be also inside that filter. Therefore, that filter belongs to A intersection B plus. Okay, so this also, there is no ultra closed filter involved here, but here when you come to open sets, we have that one. Namely, if U and V are open subsets of X, then U union V plus is U plus union V plus. Okay, so once again, if F contains this element U union V, then we know that one of the U must be inside F, which is same thing as saying F belongs to either U plus or V plus. The converse part is easy. Once F contains U, it will contain U union V, which is a superset. Similarly, if F contains V, it is superset, U plus V will be there. Okay, so this way is easier. This way needs that the criterion that we had for ultra closed filters. Okay, so this is what I have written down here. So let us go through. 1 and 2 are obvious, just set theoretic thing, definition. The third one is what I have seen, I will repeat it. F belongs to A intersection B plus. Okay, by 1, this means that A intersection B is in F. That's the definition anyway. Since F is a filter, this implies A and B are inside F because they are supersets. Hence, F is inside A plus intersection B plus. So these steps are completely reversible because if A and B are in F, intersection is there. That is the word. Okay. So the fourth statement, as I told you, it is a consequence of that proposition which gives you that U and V are open subsets. Okay, and U union V is there, then either U plus is there or not either, one of them, U or V, must be there. Okay, so this was proposition 7.64, which was proved separately for ultra closed filters. Okay, so property, this especially the 3, property 3, it just means that the family of all these A pluses, where A is an open subset of the topology on X. So this property tells you it is closed under finite intersection. Okay, so that is the important property for us. Okay, so look at B hat such that all U plus, where U is a tau now. I am not taking arbitrary subsets, I am taking only open subsets. Look at this collection. This collection has a property, it is closed under finite intersection. Therefore, it forms a base for a unique topology tau hat on Wx. Namely, all that I have to do is take arbitrary union of members of B hat, that will be topology for X. Topology for tau hat, namely topology tau hat, namely on Wx. Okay. So there are so many ways of giving topology. We have to just justify that this topology is the right one, right? So that is the task now. The set Wx with this topology tau hat generated by the base B hat is a compact T1 space. We are not so much worried about T1ness, but compactness is the first thing we need. Okay. Moreover, the function phi from X to Wx, which is set theoretic injection already, defines an embedding of phi x inside Wx. Okay, and the image phi x being dense. Okay, with phi x contained inside Wx being dense. Okay, so that will complete the statement that phi comma Wx is a compactification of X. Actually, this term says the T1 compactification. So the first thing is to see that Wx is compact. To see that Wx is compact, for any space compact, it is enough to prove that an open cover from a base, you fix one base for the topology, take any open cover from that base, members of that base. If that admits a finite subcover, then X will be compact. This is a standard result that we are going to use now. So we have fixed this base, we will take that base itself, B hat, okay, take members of B hat which cover Wx, and let us see that it admits a finite subcover. Okay, Ui, I belong to I, be a family of open subsets in tau such that Wx is union of Ui plus. In case, I am making a subcase here, in case there is a finite subset J of I such that X itself is contained inside the corresponding Uj's, okay, then it follows that by property 4, okay, this is a finite collection, so Wx is equal to union of Uj pluses, because X plus will be equal to union of Uj plus. We have proved it for 2 at a time, but that can be immediately generalized to n, any finite number, right? That is what it is. X, you take X plus is Wx, so that will be equal to union Uj plus. Now this is a finite cover, so we are done. The second case is, suppose this is not the case. What is the meaning of that? That there is no finite family out of the Uj's that are Ui's that we have chosen, okay, which will cover X. Remember, the Ui pluses are covering Wx. Now I am talking about Ui's being covering X. Why should happen? There is no need. We are not assuming X is compact after all, right? So suppose there is no such finite subcover, so that case remains. So that is the case we are going to address in a standard way. You know, this kind of argument is used several times in topology, especially when dealing with compact spaces. So we may assume that no finite subfamily of Ui cover X. By De Morgan law, this just means that the complement of this family Ui's, right, members of this family, is a family of closed sets with finite intersection property. No finite intersection of these complements can be empty because the corresponding members would have covered the X, right? So it has finite intersection property. Therefore, there exists an ultra closed filter G on X which contains the closed filter generated by this family as a subbase. Any family of members which have finite intersection property will generate a filter that is automatically closed filter because these are closed subsets. Every closed filter is contained in an ultra closed filter, and that is what I am denoting by G. Let us say that this G after all is a member of Wx, so it must be inside Ui plus for some I inside I, because Ui pluses are a cover for Wx. What does this mean? By the very definition of Ui plus, this means this Ui is inside G. Remember, G is a it is a larger filter which contains the filter generated by these elements. Therefore, all the Ui pluses are inside G. In particular, whatever Ui plus comes from here, that is also there. but ui and okay, this ui plus and its complement cannot be both be inside G. Okay, so G belongs to ui plus means that ui is inside G, right? But G contains ui complement, so that is not possible because no filter will contain both set and its complement. So compactness of Wx is proved. Let us now prove that Wx is a T1 space. That comes very easily right now. If it is not a T1 space, what does that mean? There exists a pair of points inside the space. Now they are now ultra closed filters. Distinct points means f1 is not equal to f2, such that every open set u in X, because now I am looking at basic open subsets around f1. Okay, they will be like open subsets in U and then U plus. F1 will be inside U plus, but F2 is also inside U plus. There will be such a F1 and F2. Whenever you take a neighborhood of F1, it will be a neighborhood of F2 also. So there will be such a pair. It may happen starting with F1, F2, it may not happen. Just because it's a T1, not a T1 space, somewhere it is happening. That is the whole idea. Somewhere it is happening. Okay. So F1 is in U plus implies F2 is in U plus. Okay. Now these are B plus elements of U plus or B plus. So B hat, right? I have denoted B hat. So don't get confused. Now you take B as a base for F2 consisting of closed subsets of X, because by definition every ultra closed filter must have a base consisting of closed subsets. Okay. From earlier theorem we get, if we take a member of this base C, then the complement, which is an open subset, that cannot be in F2 because the member is in F2. F2 is not in U plus is the same thing as saying that U is not in F2, right? If F2 is not in U plus, by this choice, F1 cannot be in U plus, right? F1 is not in U plus, which just means that U is not in F1. If U is not in F1, this is where I have to use this criteria. Given any open set, U or U complement must be inside the closed, ultra closed filter. So U belongs to F, U is not in F1 implies U complement, which is C inside F1. So what we have proved here? We have proved that this base, which is for F2, is completely contained inside F1. Every member is here. Therefore, the filter generated by B will have to be contained inside F1 because F1 is a filter. Okay, we started with two ultra closed filters, right? So one cannot be contained inside other, okay, or they are equal. So whichever way you are contradicting, because we have started with two different distinct ultra closed filters. Okay, so if we are just watch out this one. Okay, if you are just doing these things with just ultra filters, all right, could you have done this one? Can you get this? You keep examining these kind of things. So where is really the role of ultra closed filter is coming up? Okay. To show the continuity of E is the next task. And then there will be one more, namely to show that phi is a closed map or an open map. That will complete the embedding. Okay, finally we have to show that it is dense also. Yeah. So to show that phi is continuous, it is enough to show that inverse image of basic open sets is open. Okay. So if you take a basic open set, it will look like U plus, where U is an open subset of phi. Okay. And U is an open subset, U is an open subset of X. Right? What is phi inverse of X? What is phi inverse of U plus? Remember, what is phi? Phi is X going to Fx, where Fx is the atomic filter. So start with an atomic filter, it will come from X, because there is 1-1 mapping, right? So phi inverse of U plus will be just a point there, and that point must be inside U, right? Because U belongs to Fx if and only if X belongs to U. So these are just, phi inverse of U plus is just the original set U, right? So in U is open. So continuity of phi follows. Not only that, you observe this just means that U plus intersection phi X is precisely phi of U, because inside phi X we only have the atomic filters. The atomic filter containing the whole of U just means that X is inside U. So it is phi U. Phi U is equal to U plus intersection phi X is stronger than just saying this one, but because this is just an embedding, these are all okay. Now this I can use this one again. It remains to show that phi X is dense. But once again, it is enough to show that phi X meets every member of B hat. You see, phi X is dense means it should meet every non-empty open set. But inside a non-empty open set, there will be some member of B hat, right, base. So if it means basic open set, that is enough, right? This follows from this equation. Take any basic open set, phi of X intersection U plus is phi of U, so it is non-empty. Over. So this just equation proves density, continuity, as well as openness. Take an open set, any open set of phi, okay, image of phi is U plus, which is an open set, intersection phi X. So it is inside phi X it is open, phi U is open. By definition, phi X, the image of phi X, takes the topology, the induced topology, everything is open if and only if it is intersection of an open subset inside the larger space. So this proves the openness, it proves the continuity as well as density. So those things are very easy to obtain. So let us complete now the definition of Wallman compactification. As I told you earlier, a compactification is a certain equivalence class, right? But here we are usually taking one particular representative all the time. Okay, anything which is equivalent to this one will be also called Wallman compactification in general. So here we have, first of all, what we have, starting with any T1 space, we constructed this Wx, which is just the collection of all ultra closed filters on X with a very specific topology, with the base consisting of U plus, where U is open subset of X. Okay, so that compact space along with the embedding of X inside that, this is called Wallman compactification of the T1 space X. you can remember that Wx is automatically T1. So here are a few remarks. The T1ness of x is only used in getting the function phi from x to Wx. Okay. Why? Because I start with x and then I construct fx. But why should fx be an ultra closed filter? It is an ultra filter. Why it's closed? That's where I have used that x is T1, so singleton x is closed. So singleton x is the base for the whole of fx. Any atomic filter, it's a base. So that is one way immediately to get the function itself we have used. Automatically it is injective. Okay, there is no problem. Whereas the topology on Wx is always T1. The T1ness of x is not used in this one. Okay. One does not know when this topology on Wx is Hausdorff. Why I am making this comment? Usually one would like to know, because we are in some sense obsessed with Hausdorffness. So would it be Hausdorff under some suitable nice condition? If it's freely T1, by putting little extra condition, maybe you will get its Hausdorff, right? But here I am saying that one does not know when this topology on Wx is Hausdorff. So next time we shall continue to study the universal property of Wallman compactification. Remember the universal property of Stone-Check compactification, and there is a universal property of even some kind of universal property of one-point compactification also. This will be somewhat similar to that. Of course, in each case it will be slightly different. Okay, thank you.